There's this vibe in the agentic world that more agents equals better performance. Like take a single agent, split it into a team, let them collaborate, and you get a free uplift. Today, I'm breaking down a Google Research and DeepMind paper from late 2025 called Towards a Science of Scaling Agent Systems. This paper basically says not only is that not reliably true, but we can actually predict when multi-agent systems will improve over a single agent and when they will degrade, especially as you scale. And that's the main thing to understand. We are not just comparing multi-agent versus single agent. We are predicting how multi-agent systems degrade or improve relative to a single agent baseline when we scale them. What this paper claims to deliver is a model for predicting the performance of your agent architecture at scale, a quantitative model that says, given a task, given a coordination structure, given model capability, and given behavioral signals, we can measure at runtime. Here's what happens when you add agents. Before this, a lot of AI agent work has basically been heuristic driven. Frameworks and demos popularize the notion that multiple agents are always better than one. But a lot of the research and practice has been vibes-based. This paper addresses that gap by trying to produce quantitative scaling principles for agent systems. And from an enterprise perspective, I think this matters more than it sounds because you don't own the foundation models. You do own the orchestration. So if the orchestration choices have measurable effects, that's actually actionable. Now, how do you frame scaling laws in this context? They characterize scaling laws as the interplay between four things: agent quantity, coordination structure, model capability, and task properties. And importantly, they do not just label a system as multi-agent and call it a day. They model behavior at runtime using metrics collected from real executions and then fit a predictive model to those behavioral signals. So how do they build a data set? They evaluate agent system performance across four benchmarks: Plancraft, Workbench, Finance Agent, and Browse Com Plus. So you're covering game planning, workflow execution, financial reasoning, and web navigation. Then they test 5 architectures. This is the bit that matters if you're building real systems because architecture is what you actually control. There's a single agent system, and then there are 4 multi-agent coordination structures. I'll define those for clarity. Independent. Agents work separately and you aggregate outputs. Decentralized. Peer-to-peer collaboration. No master orchestrator. Centralized. Routing through an orchestrator agent. Hybrid. A mix of hierarchy and lateral communication. Those are the multi-agent system types in this paper's setup. Then they instantiate these across 3 model families. In the setup, that's OpenAI, Gemini, and Claude families. So overall, they construct a grid, 9 models across 3 families, times 5 architectures, times 4 benchmarks. That is 180 configurations. This is a grid, not a set of cherry-picked examples. And the key thing, so we don't get lost in the detail, is that they try to isolate the architectural effect. They standardize tools, prompt structures, and token budgets across conditions. So they are basically ruling out better prompting, better tools, and more inference budget as the reason performance changes. They're trying to isolate what the architecture itself is doing. Next, we need to be clear about what they mean by single agent versus multi-agent, because the trade-off is the foundation of everything. A single agent system has one reasoning locus. It is one sequential loop: reason, act, observe, repeat, all in one coherent memory stream. A multi-agent system splits reasoning across multiple LLM-powered agents who communicate via messages, shared memory, or an orchestrated protocol. And here's the paper's framing. A single agent system maintains coherence because the full working context is in one thread. Multi-agent systems introduce fragmentation by design. That fragmentation can be good because you get diversity of exploration, parallel search, separate perspectives, but it introduces an unavoidable coordination tag. Global context has to be compressed and communicated across agents. That compression is lossy. Then you get synchronization overhead, the extra cognitive load in the system, more failure surface area. So the question is, when does the benefit of parallelism beat the coordination tax, and when does it not? Now, here's the most important methodological part of the paper. They build a predictive model using runtime behavioral signals they call empirical coordination metrics. These are measured during execution, not guessed up front. The key metrics are coordination overhead, message density, redundancy rate, coordination efficiency, error amplification. Let me translate those into what they mean operationally. First, coordination overhead. How much extra work the team creates compared to a single agent. Token spent on syncing, handoffs, summaries, orchestration. Second, message density. How chatty the system is. Are the agents mostly thinking and acting or mostly talking to each other? Redundancy rate. Are the agents actually contributing different thinking, or are they repeating the same outputs in different words? Fourth, coordination efficiency. How much useful task progress you get out of coordination relative to the extra cost that coordination introduces. Fifth, error amplification. This can be thought of as, does collaboration correct mistakes or does it actually spread them? And the subtle but important point is these aren't theoretical labels. They're runtime behaviors. You can measure them in a real system, and that's what powers the paper's scaling model. This is a behavioral model of agent systems at runtime. It is not just architecture label in, performance out. It is behavioral signals in, performance out. Now, the paper also makes a big deal about what counts as an agentic task. They argue that previous studies often evaluated agent architectures on tasks that aren't truly agentic. So they provide a definition. An agentic task requires sustained multiple-step interaction with an external environment, iterative information gathering, partial observability, and adaptive strategy refinement based on feedback. If you want to conceptualize this, think about navigating through a maze. That can be thought of as an agentic task. On the other hand, summarizing a document is not. There are agentic tasks that do not involve physical movement. Bear this in mind. Because in agentic tasks, environment feedback changes the dynamics. Error propagation matters more. Coordination overhead matters more. Small mistakes compound across multiple step chains. So the paper is trying to model real-world deployment regimes where feedback matters, web navigation, workflow execution, financial analysis, and so on. Now, the experiments are designed around 3 research questions. First, what factors determine agent system performance, model capability, coordination architecture, task properties, and interactions? Second, under what conditions does inter-agent coordination improve or degrade performance? Third, and this is the main one in my opinion, can we derive quantitative scaling principles that predict the best agent architecture for a given task based on measurable properties? The third research question is the heart of it because it suggests a more rigorous way to build agent systems. Instead of saying some multi-agent system is better for X, it suggests you should measure coordination behavior, extract continuous runtime metrics like overhead and efficiency, and use those to predict how performance changes when you scale. Architecture shifts from being the explanation to being the cause of measurable coordination behaviors, which then explain performance at scale. The model itself, in simplified form, is basically performance equals a baseline plus model capability plus single agent baseline plus coordination efficiency minus coordination overhead minus error amplification minus redundancy plus interaction terms. And the line you should remember is all the interesting scaling behavior lives in the interaction terms. Those interactions are where you see why something looked fine in a small demo, then collapses when you scale tool use, depth, or agent count. So what do the results say? The first big result, multi-agent performance is domain dependent. Contrary to the conventional wisdom, multi-agent systems do not always beat single-agent systems. It depends heavily on the task, especially whether the task can be decomposed. Finance agent is a clean example where a multi-agent system can outperform baseline being the single-agent system, because the task structure decomposes naturally into parallel streams. You can research filings, you can scan merger news, you can assess operational impact, you can do regulatory and competitive context, then synthesize. A single agent struggles to cover that breadth within budget. Multi-agent systems can because parallelism matches the task structure. In contrast, Planecraft is an example where multi-agent can fall apart, because Planecraft is sequential and interdependent. One step depends on the previous step. There is depth, state tracking, constraint verification, and if you split that across agents, you can create redundancy and coordination overhead that eats the budget. You end up with agents coordinating on things that did not need parallel decomposition in the first place. So the paper's practical framing is, when coordination complexity exceeds task complexity, multi-agent can degrade relative to single agent. But when a task naturally decomposes into parallel information streams, multi-agent can improve. The second result, domain complexity moderates coordination efficacy, but it is not the full story. In structured decomposable domains, agents can complete their local reasoning with enough residual capacity to communicate and coordinate. But in deeply sequential domains, intra-agent reasoning can dominate token consumption before coordination even has room to work. Coordination quality collapses downstream, and the key nuance, it is not just complex versus simple. Can the task be split into parallel, mostly independent steps? The third result, architecture by model family interactions exist, and they are vendor specific. Two key intuitions come out here. No model vendor shows universal multi-agent dominance, and all vendors experience performance collapse when multi-agent is applied to the wrong task structure. In particular, deeply sequential, tightly interdependent tasks show systematic degradation under multi-agent systems across families. And yes, some model families scale from single agents to multi-agent better than others. That seems tied to the intrinsic behavior of the base model, not just task complexity. Now we get to the scaling laws and the interaction effects, because this is where the paper gives you the why. They fit a mixed effects model with both main terms and interaction terms. The full equation is big, but you do not need to memorize it. What matters is which interaction terms are significant and strong, because those are your failure modes. 3 interaction terms dominate. First, coordination efficiency times tool complexity. This is a tool coordination trade-off. A multi-agent system can look excellent when tool complexity is low and coordination is efficient. But as tool complexity increases, more tools, more tool calls, more branching, more state transitions, that coordination efficiency multiplied by that tool interaction predicts a performance dip, because the coordination costs and tool overhead compound. So you can build a multi-agent demo that looks great at a low tool count, then it drops as soon as you scale tool use. Second, coordination overhead times tool complexity. This is basically saying overhead is not just a constant penalty. It gets worse as tasks become more tool heavy and deeper. Third, and to me the most interesting, single agent baseline times the log of agent count. This is the baseline paradox. The better the single agent baseline already is, the more quickly multi-agent systems lose their advantage as you add agents. Intuitively, if your single agent is already strong on the task, there is less headroom, left for multi-agent coordination to add value, and coordination costs start to dominate sooner. And I think they track this in the paper at around 45% on performance benchmark. This is basically coordination saturation. So a key takeaway is, if your single agent system is already doing well, adding agents can be the fastest way to make it worse. There are secondary effects too. For example, redundancy times agent count can show a small ensemble benefit, meaning a bit of overlap can help as you add agents, but it tends to be at modest compared to core interactions. In the paper's reported results, they also note that the model hits around 87% accuracy on selecting the optimal architecture. I do not take this as, look how prophetic the model is. I take it as evidence that these scaling laws are capturing real structure, at least across the regimes they tested. So what's my overall conclusion and what do I take from this? To get agents to scale effectively, you cannot treat architecture as a cosmetic choice. You need to consider together runtime, observed coordination metrics like overhead and efficiency, upfront system design choices, single agent systems versus multi-agent systems, and the coordination structure of those systems. And task structure, especially decomposability, tool complexity, and depth under feedback. This paper gives you a model for understanding failure modes as you scale. For example, it suggests that once a single agent baseline crosses a certain threshold, adding more agents can produce diminishing returns and then deterioration. It also gives you a way to understand why some multi-agent systems work well in demos but fall over at production scale, especially when tool use grows. Now, there are limitations, and I think it is important to be honest about them. One big caution: the tasks they use are agentic tasks as they define them. So you should not take this model and apply it to document summarization and pretend it transfers. If you want to leverage these insights, tasks like financial analysis, web navigation, workflow execution, and multi-step environment interaction, because that's the regime the model was built on. Another subtle limitation: they kept prompts consistent across architectures by design. That isolates architectural effects, which is exactly what they wanted. But it also means prompting strategies that are tailored to specific architectures were not explored here, and that could change outcomes in practice. So the practical advice I'd extract is, do not fall into the trap that more agents are better. Treat multi-agent as a tool that only wins when task structure supports parallelism and decomposability, and when coordination overhead is controlled. If you're building for production, the sensible workflow is understand the task structure up front, pick architectures that match that structure, run small-scale experiments across a few model families and coordination structures, measure runtime coordination behavior, then use the scaling laws to predict what breaks when you scale. That is the difference between agent systems that look good in a demo and agent systems that survive production scale.